Hi, welcome back to Calculus. Today we're looking at some integration with trigonometry. Um, so we're going to use a lot of identities here in this particular section. And one of the big ones that we're going to use is one of the real basic ones, sine squared x plus cosine squared x is equal to 1. So we want to start with integrals of the form where sine and cosine are raised to powers. So you can see I'm looking at integrals of the form sine to the m of x times cosine to the n of x dx. So we're going to break this into three cases. The first two cases are really basically the same thing. The third one is a little bit different. So the first two cases deal with one of those powers being odd. So in this case, m is odd, and you can see I'm looking at the integral of sine cubed x times cosine squared x dx. And all we're going to do with these is take advantage of the fact that sine and cosine are derivatives of each other. And so a really good way to think of this is that since I have a third power, I can peel off one of those signs and have it just kind of hanging out there. And the advantage is that sine is, well, negative sine is the derivative of cosine. So if I can turn all of this into cosines, I have a ready-made substitution. And so that's what we're going to do. I'm going to use that kind of Pythagorean identity, sine squared plus cosine squared is equal to 1. And I want to substitute for sine, so if I subtract that cosine squared, I get 1 minus cosine squared x is equal to sine x. And so I distributed this and got the integral of cosine squared x minus cosine to the fourth x. And you'll notice I'm just leaving that sine x hanging out there at the end all by itself. That's because now I'm going to do my substitution. If I call u cosine, then du is negative sine. And all that means is I get u squared minus u to the fourth. And then I do pick up a negative here from the derivative. So I get a negative du. And if you distribute that negative, we have negative u squared plus u to the fourth. And I need to integrate that. But that's easy. That's just a polynomial. We're good at those. So I raise the power and divide. So I get negative 1/3 u cubed plus 1/5 u to the fifth plus c. And then I bring back my cosines. And I have my answer. So for a lot of these, actually, they can both be odd, it really doesn't matter. But if at least one of these is odd, we can do basically that same kind of thing. So I'm going to do another example where this time the cosine will be odd, and we'll make that one work. And you'll see that it really works very similarly to this one. All right, so let's look at another example. This time we're going to have the power on cosine be odd. But again, it's going to basically work the same way. We're going to use a Pythagorean identity again, and it's going to work itself out nicely. So this time you can see over here I have the integral of cosine to the 7th x dx. No signs, that's okay. We have an odd power on the cosine. All I'm going to do, same thing as last time, I'm going to peel off one of those so that I have a bare cosine sitting there all by itself. I then have cosine to the 6th times cosine. Well, cosine squared is 1 minus cosine, cosine squared is 1 minus sine squared. So I can think of this cosine to the 6th as 1 minus sine squared cubed, right? This is cosine squared, 2 times 3 is 6, so I have the right powers. And now I'm going to do my substitution. I'm going to let u this time be sine, and du is cosine. So I get the integral of 1 minus u squared to the third power, and cosine x dx, it just all turns into du. If you multiply this set of parentheses out, be very careful, you get the integral of 1 minus 3u squared plus 3 to the fourth plus u to the sixth du. And then we take all of our antiderivatives, so we get u minus u cubed plus 3/5 u to the fifth plus 1/7 u to the seventh plus c. And last but not least, turn all those u's back into signs. And so there we have it. The answer looks horrible, but it's really not that bad to get. So as long as one of these powers is odd, these really work out pretty nicely. So next up, we're going to look at what happens if they're both even. Because if they're both even, this isn't going to work nearly as well. So this example ends up enormous. So in just a minute, I'm going to have to actually move my camera so you can see the end of the problem. So case 3, both are even. So this time, we're going to work with these identities. Sine squared is equal to 1 minus cosine 2x over 2, and cosine squared is 1 plus cosine 2x over 2. So here's my example. Sine to the fourth times cosine squared x dx. So I immediately go ahead and make these substitutions. Sine squared is 1 minus cosine 2x squared, but I need a square here because it was a fourth power, right? 2 times 2 would be 4. And then for the cosine squared, 1 plus cosine 2x over 2. Very first thing I do is I pull out these 2's on the bottom. Don't forget this one's a 4, because 2 squared is 4. So 4 times 2 gives me an 8 out front. And then I multiply what's left out, and if you trust me, it ends up being 1 minus cosine 2x minus cosine squared 2x plus cosine cubed 2x dx. And at this point, this is where it's really going to get kind of bonkers. There's a lot of mess going on here. Now, some of it's really straightforward. For instance, we know the antiderivative of 1 is just x, so I get a 1/8 x. We can very quickly do the antiderivative of negative cosine. That's going to be negative sine. We do have to multiply by a half for the chain rule with that 2 on the inside. So 1/8 times a half gives me minus 1/16 2x. But the real fun here is going to come with these last two pieces. The cosine squared 2x and the cosine cubed 2x. So you can see I brought it over and I rewrote it with those two integrals, or with those two pieces being integrated separately. So I have my minus 1/8 in antiderivative of cosine squared 2x dx and my plus 1/8 cosine cubed 2x dx. And then what I did, oh, you can't see it now. So let me bring this over. There, now we should be able to see it. Perfect. So then what I did is I took each of those integrals separately. So I wanted to integrate, and I really should have just put the 1/8 in here, but I didn't. So we'll have to deal with that 1/8 when we come back. But I did do the negative. Anyway, so I dealt with the cosine squared 2x. I used that reduction formula again. The cosine squared of x is 1 plus cosine 2x over 2. But this time, since I already had 2x on the inside, I get a 4x. I also brought the half out, and then I took an antiderivative. Antiderivative of 1 is x, so I get a negative half x. When I multiply it by the 8th that was still over here, I get a negative 1/16 x. And then for the cosine of the fourth, I keep that half. That was a minus. Let's change that to a minus. I keep the half, but now I have to multiply by a fourth for that chain rule. So I get a minus 1/8 sine of 4x. And if you multiply that 1/8 times 1/64, you get a minus 1/64 sine of 4x. So we're having lots of fun. But that's the first, where am I? Right here. That's all the way through this integral right there. All that's left now is to do the cosine cubed. But we just did stuff like this, right? This is a cosine to an odd power. And so I'm going to repeat that exact same trick. Here I have it. 1/8 times the integral of cosine cubed 2x dx. I broke it into cosine squared and peeled off that single cosine. I changed my cosine squared to 1 minus sine squared 2x because now the derivative of sine is cosine, and I do my substitution. I let u be sine 2x, du then is a half cosine 2x dx. If you multiply both sides by 2, you get a 2 that comes out when you make the substitution, so we get a fourth, and I have 1 minus u squared, and that integrates beautifully because now it's just a polynomial. So you can see I ended up with 1/4 u minus 1/12 u cubed. I brought it back and put in sine of 2x's for both of those. And then the last thing that you would really want to do here is if you have some like terms, this 1/8 x and the minus 1/16 x. Let's see, the minus 1/16 sine 2x and plus 1/4. So you want to put those back together. But there you go. So these just end up being really big and really messy. All right, we have a little bit more to look at here with these trig things. So great. So here we have a pretty quick little example. I didn't bother to keep going because what comes next takes more space. I just want to integrate from 0 to pi over 4, the square root of 1 minus cosine 4x dx. And so we're going to use one of those same trig identities that we've worked with before. We know that sine squared is 1 minus cosine 2x over 2. So sine squared of 2x is 1 minus cosine 4x over 2. So I just multiply both sides by 2, and that allows me to replace the 1 minus cosine 4x with 2 sine squared 2x, which is great because 2 is just a constant, so I can pull that square root of 2 out front, and the square root of a square is just the thing on the inside. So we get square root of 2 times the integral from 0 to pi over 4 of sine 2x dx, and that's beautiful because the antiderivative of sine is cosine, negative cosine. So I get negative cosine 2x over 2 because, again, we have a chain rule. So I pulled the negative and the 2 out front. So I get negative square root of 2 over 2. And then I plugged in those numbers. If you plug in pi over 4, 2 times pi over 4 is pi over 2. So I get cosine of pi over 2 minus cosine of 0 when you plug that in. And cosine of pi over 2 is 0. Cosine of 0 is 1. So this all just works out to be negative 1. And negative 1 times that gives me positive square root of 2 over 2. All right, let's get into tangents and secants. So here we're going to start looking at tangents and secants. I have some useful things here over at the left. Tangent squared is equal to secant squared minus 1. Just adding 1 to both sides gives us that secant squared is equal to tangent squared x plus 1. And then I have the derivatives for these. The derivative of tangent is secant squared, and the derivative of secant is secant times tangent. So we're going to take advantage of that. Let's do this one. Tangent to the fourth, secant to the fourth. So when I look at this, what I really want is to be able to make a substitution and have this work out really nicely. So what I did is I said, okay, secant to the fourth is the same as secant squared times secant squared. And that's useful because secant squared is the derivative of tangent. So I'm setting myself up for some substitution here. Before I can do that, though, I need to get rid of the other secant squared, but very conveniently, secant squared, which is the plus 1. Secant squared is tangent squared x plus 1. And then I did a substitution. I said, okay, let's let u be tangent, and du then is secant squared x dx. So what do I end up with? That should be a plus. What do I end up with? I end up with an antiderivative of u to the fourth times u squared plus 1 du. Multiply that through, we get u to the sixth plus u to the fourth, and when we take its antiderivatives, we get 1 over 7 u to the 7th plus 1/5 u to the 5th plus c. Don't forget that constant. This is an indefinite integral. And we put the tangents back in, giving us our answer. All right, almost there. One more. All right, so for our last one, we're working with multiples of sines and cosines. So you can see here I have sine 6x times cosine 5x. All right, the problem is the numbers on the inside are different, so we can't just use a basic substitution. Turns out it's actually really not bad, but we do need one of these 3 identities. So we have the sine of mx times the sine of nx is a half times the cosine of m minus nx minus cosine of m plus n. Now the good news is just numbers. So m minus n is easy to find, m plus n is easy to find. Sine mx cosine nx is a half times the sine of m minus nx plus the sine of m plus nx. And if they're both cosines, cosine of mx times cosine of nx is a half times the cosine of m minus nx plus cosine of m plus nx. All right, so what does that mean for this? Well, once we identify m and n and which version we have, in this case we have the second one, we go through, we need an m minus n, so 6 minus 5 is 1, and we need m plus n, 6 plus 5 is 11. And then I just pulled that half out, and so we have the sine of 1x plus the sine of 11x. And those are really nice little integrals to find. Antiderivative of sine is negative cosine, so I get a negative half cosine x. For the sine of 11x, we have to work just a little bit harder because we do have a chain rule there. But I get the same kind of thing. I get a negative half because, again, the antiderivative is going to be a negative cosine. But I do have to multiply by 1 over 11 to take care of that 11 that was on the inside. So we end up with negative 1 over 22 cosine 11x and then plus c. So those are really nice. I like those a lot. Have a wonderful day.